How to turn a number system into a geometric space. Our goal is to introduce the concept of a scheme. It was introduced by Alexander Grothendieck in 1960. He was considered to be the Einstein of math, and for good reason. His concept of schemes revolutionized algebraic geometry, and we're about to find out why. What are schemes used for? Schemes are used to do geometry over the integers, the p-adics, and other number systems. Schemes can remember more things. For example, the equations x equals 0 and x squared equals 0 have the same set of solutions, but result in different schemes. This is called non-reducedness, and is useful for intersection multiplicity. For example, the two lines intersect the parabola, but one is tangent and the other crosses it. Thus, they result in different schemes. As you can see, their intersections are different. The first one has x minus 1 squared, and the second only has y minus 1, no squared. Schemes are also used in the proof of Fermat's last theorem by Andrew Wiles. For example, Wiles used properties of representations associated to a special kind of scheme, finite flat group schemes, over the p-adic integers. So, what are you waiting for? Let's get started. There are many examples of geometric spaces, such as a plane, a torus, a sphere, and so on. Let's look at a simple example, R2, the plane. Consider continuous functions on the plane, such as f of xy equals 3x plus 2y. There is also a topology, a notion of nearness, and a concept called open sets. A set is open if, given a point in that set, you can move it slightly and stay in the set. Here's the formal definition of an open set in a metric space such as Rn. A set is open if, given a point in the set, there is some epsilon greater than 0 which can depend on the point, such that if you move the point by a distance less than epsilon, you stay in the set. Some properties of open sets are: the empty set is open, the entire space is open, the union of any collection of open sets is open, and the intersection of two open sets is open. As an exercise, prove these properties for Rn. Now we get to an important definition. A topological space is a set, along with a collection of subsets called open sets, such that these four properties hold. A closed set is a set where the complement is open. Now let's talk about continuous functions. A continuous function is one where a small change in the input results in a small change in the output. That is, if U is an open set in the output space, then its preimage is open in the input space. Here's the formal definition of a continuous function. Basically, it states that the preimage of an open set is open. And here's the intuition behind the definition. It reflects the idea of small change in input, small change in output. That's it for topology. Now, let's move on to number systems. In the integers, we can add, subtract, and multiply, but we can't necessarily divide, since 1/2 is not an integer. The integers is an example of a commutative ring, which means we can add, subtract, and multiply, and they behave the way that we expect them to. Here's a list of properties that a structure must satisfy to be a commutative ring. The ring axioms basically say that you can add, subtract, and multiply, and they behave like normal. Examples are the integers and polynomial rings. And an example of a non-commutative ring is the ring of 2 by 2 matrices. It is not commutative because A times B is not always equal to B times A. Warning! In this video, every time I say ring, I mean commutative ring, but this is technically inaccurate, so keep that in mind. There is also a notion of good functions between commutative rings called homomorphisms. They are functions that preserve addition, multiplication, 0, and 1. Some subsets of rings, such as the multiples of 4, have nice properties. The sum of two multiples of 4 is a multiple of 4, and a multiple of 4 times any integer is also a multiple of 4. Such subsets are called ideals. Here's the formal definition. 0 is in the ideal, the sum of two elements in the ideal is also in the ideal, and an element in the ideal times any element of the ring is also in the ideal. In the integers, we can take remainders mod 4. Can we do this in any ideal of any ring? Yes, we can define an equivalence relation corresponding to any ideal, such that A is equivalent to B if and only if A minus B is in the ideal. the set of equivalence classes is called a quotient ring. As its name suggests, it's a ring. Try defining addition and multiplication and show it's well defined. Now let's connect rings to topology. We can add and multiply continuous functions together so they form a ring. Given an inclusion of open sets V subset U, we can restrict continuous functions from the bigger set to the smaller set. This is a ring homomorphism. So we have a ring for every open set and a ring homomorphism for every inclusion of open sets. Thus, the continuous functions form something called a sheaf of rings. Here's the definition. Basically, it means that we have a ring for every open set and a ring homomorphism for every containment. They satisfy the properties shown here. First, the ring associated to the empty set is the zero ring. Second, restricting twice is the same as restricting once. Third, the uniqueness axiom. If two elements in OX of U have the same restrictions on an open cover, then they are the same. Fourth, the gluing axiom. If we have elements of OX of UI that agree with each other on overlaps, then we can glue them together to get an element in OX of the union of all the UIs. Now, consider these two functions. They are equal when the point is inside the circle. How can we express this relationship? To do so, we use the notion of a stalk. It's a way of zooming in at a certain point. Here's a formal definition in terms of equivalent classes of pairs UF, where U is an open set containing the point X and F is an element of OX of U. Intuitively, it means that two elements of stalk are equal if they agree in an open set containing X. Elements of the stalk are called germs. In the previous example, for any point X in the circle, there is some open set containing X, and F and G are equal when restricted to that open set, namely the circle. Thus, F and G are equivalent in the stalk at X. Now, suppose F is a continuous function and f of x is not equal to 0. Then, since f is continuous, there is some open set U where f is nowhere 0. 1 divided by f is well defined on U, and f times 1 over f is equal to 1. Recall the definition of a stalk. Thus, if UF is an element of a stalk near X and f of x is not equal to 0, then UF is invertible in the stalk at X. An invertible element of a ring, otherwise known as a unit, is an element A of the ring such that there exists another element B such that A times B is equal to 1. Note that the sum of two non-invertible elements is not invertible. This means that the stalk is a special kind of ring called a local ring. A local ring is a non-zero ring where the sum of two non-invertible elements is not invertible. As we have just seen, the stalk is a local ring. This brings us to a very important definition, a locally ringed space. It's a topological space with a sheaf of rings called the structure sheaf, such that the stalk at any point is a local ring. We have just seen that any topological space with a sheaf of continuous functions to R is a locally ranged space. Other examples include a manifold with a sheaf of smooth functions, a complex manifold with a sheaf of holomorphic functions, and a scheme which we are about to define. We can now make our goal more precise. We started out asking how to turn a number system into a geometric space. Our precise goal is how to turn a commutative ring into a locally ringed space, such that the ring is a ring of functions on that space. The locally ringed space we will define is called Spec R. It has the nice property that the ring of global sections is R. In other words, the ring associated to the entire space is R. First, let's talk about the points. Let big X be a topological space and little x be a point. The set of all functions that are 0 at X is an ideal of the ring of continuous functions. As an exercise, try proving it's an ideal. Here's the definition again. The set of functions that are not 0 at a certain point is a very special kind of ideal. It's a prime ideal. A prime ideal is an ideal that is not the entire ring, and the product of two elements that are outside of the ideal is also outside of the ideal. Since prime ideals are so closely related to points in topological spaces, let's define it that way. A point of spec R is defined to be a prime ideal of R. Define the value of an element A and R at P to be the equivalence class containing A in the quotient ring R quotient P. Now let's talk about the topology of spec R. Recall the definition. Given a continuous function, the set of all points where it isn't zero is an open set. On spec R, we have a notion of the value of a function at a point, so let's define open sets that way. Define d of A to be a set of points where A doesn't take the value 0, or, in other words, d of A is a set of prime ideals that don't contain A. These sets form a base of the topology. That is, U is open if, for every point in U, there exists a set of the form d of A that contains a point and is a subset of U. We can also consider the opposite notion as well. The set of points where a continuous function is 0 is a closed set. Based on this, for an ideal I of R, we define V of I to be a set of points where every element of I is 0. A set is closed if and only if it's of the form V of I. As an exercise, try proving that these two definitions are equivalent and that they satisfy the axiom of a topology. Now let's define the structure sheaf. What are the good functions on an open set U? On d of A, we should be able to divide by A, so it should be the ring R, but with 1 over A added to it somehow. This leads to the notion of localization. A subset of a ring that contains 1 and closed under multiplication is called a multiplicative subset. We can now add inverses to all elements of S as follows. Consider pairs AB representing A divided by B and give it this equivalence relation. The equivalence relation comes from our intuition involving fractions, but it's slightly modified to work for rings in general. As an exercise, try defining addition and multiplication on the localization of R at S. Note that the set of all multiples of A is a multiplicative subset. If we localize at it, we can divide by A. We can now define the structure sheaf as follows. On d of A is R localized as a multiplicative subset of all powers of A. The intuition is that on d of A is never 0, so we should be able to divide by A. Thus, we want OX of d of A to be R, but modified in some way so that A is invertible. That's what localization does. Another way to construct the localization is to use a quotient of a polynomial ring. We add a new element called x to the ring and declare that A times x is equal to 1. Since open sets of the form d of A form a base of the topology, the condition that OX of d of A equals R localized at A uniquely specifies a sheaf. We can also localize at a prime ideal. The set of all elements outside of a prime ideal is multiplicative by definition of prime ideal. This is called the localization at a prime ideal. We can describe the structure sheaf for an open set in general as elements that are locally quotient in the sense shown here. Essentially, an element of OX of U can be evaluated at a point P in U to get an element of R localized at P. It has to be locally quotient, which means if S in OX of U and P in U with S of P equals A divided by B, then S of Q is equal to A divided by B for all prime ideals Q in some open set V containing P. We did it! We constructed spec R as a locally ranged space by describing its points, topology, and structure sheaf. Let's do an explicit example. The integers. It's a principal ideal domain, so every ideal is the form multiples of n for some integer n. Which of them are prime? For positive n, multiples of n form a prime ideal if and only if n is prime. But 0 is also a prime ideal. So the prime ideals of Z are 0 and a prime ideal for every prime number. Now let's look at the topology. Remember that the closed sets are the sets of the form V of I where I is an ideal. What is V of n? Well, n is in a prime ideal P if and only if n is a multiple of P. So V of n is a set of all prime numbers that n is divisible by. Thus, the closed sets are the finite subsets of non-zero prime ideals and the entire space. Now, which closed sets contain the zero ideal? If 0 is in V of I, then I must be 0, so V of I is all of spec Z. This means the zero ideal is an example of something called a generic point. A generic point of a topological space is a point P such that the only closed set containing P is the entire space. Now let's look at the structure sheaf of spec Z. On D of n, we know that it is the integers adjoin 1 over n. Since Z is an integral domain, the localizations of Z are subrings of Q. Thus, on D of n, the value of the structure sheaf is a set of fractions that can be written with the power of n as a denominator. As an exercise, try doing the same for a polynomial ring. In one variable, it's very similar to what we have done so far, because just like spec Z, the polynomial ring in one variable is also a principal ideal domain. In multiple variables, you'll find that a subset of our prime ideals is naturally in bijection with the n tuples of elements in the field. This gives a correspondence between scheme theory and classical algebraic geometry. The next topic is morphisms of locally arranged spaces. Think back to the example with continuous functions. Given a continuous function f from x to y and g from y to z, we can compose them to get a continuous function x to z. If the third topological space is the real numbers, then for every open set U, we get a ring homomorphism from the continuous functions U to R to continuous functions f inverse of U to R. This ring homomorphism, called pullback, has a property that it commutes with restriction. That is, in this diagram, both ways of going from the top left to the bottom right have the same result. The pullback also has a nice property involving stalks. It sends non-invertible elements to non-invertible elements. We define a morphism of locally arranged spaces based on this concept. It's a continuous function f, and for every open set U of y, a pullback ring homomorphism that commutes with restriction, and has a nice property with stalks. It sends non-invertible elements to non-invertible elements. As an exercise, try to define the composition of two morphisms. Two locally arranged spaces are isomorphic if there are morphisms between them that invert each other. A scheme is a locally arranged space that is locally isomorphic to spec R for some ring R. Schemes that form spec R are called affine schemes. We did it! We just defined a scheme. A morphism scheme is a morphism of locally arranged spaces that we defined previously. Now let's talk about how ring homomorphism induces morphism of schemes in the opposite direction. If f from R to S is a ring homomorphism and P is a prime ideal of S, then its preimage is a prime ideal of R. This gives a function spec S to spec R. As an exercise, show that this is continuous. Hint, try to prove that the preimage of D of R is D of F of R. Note that this is false if we consider maximum ideals instead of prime ideals. This is why we define the points of spec R to be prime ideals. Here's another exercise. Try defining the structure sheaf pullback morphism. Hint, on D of A to D of F of A, it's R localized at A to S localized at F of A. Try x divided by y goes to f of x divided by f of y. Show how this extends to a pullback morphism on arbitrary open sets. Let's briefly talk about some more advanced topics. There are some special kinds of schemes called reduced, irreducible, and integral schemes. A reduced scheme is one where the ring for every open set has no non-zero nilpotents. An irreducible scheme is one where there are no disjoint non-empty open sets. An integral scheme is a scheme that is both irreducible and reduced. This is equivalent to OX of U is an integral domain for all non-empty open sets U. There is a construction called a fiber product of schemes that allows us to, in a sense, multiply schemes together, just like how we can take Cartesian products of sets. If a ring has a notion of degree on it, it's called a graded ring, and we can do a construction called Proj R to turn it into a scheme that has different properties than spec R. For example, Proj R is proper. A proper scheme is a scheme that satisfies an analog of compactness. There is a sheaf version of module over a ring, called the sheaf of modules. Just like how we can turn a ring R into a scheme, we can turn a module over the ring R into a sheaf of modules over spec R. A sheaf of modules that is locally of this form is called a quasicoherent sheaf. An invertible sheaf is a quasicoherent sheaf that is locally isomorphic to the structure sheaf. They form an abelian group under the tensor product called the Picard group, which is an important concept in algebraic geometry, and is also related to algebraic number theory in the sense of the ideal class group. The ideal class group of the ring of integers of an algebraic number field is the Picard group of the spec of the ring of integers. A discrete valuation ring is a special kind of local ring with a valuation on its elements that has a notion of valuation, or how often is this element in the maximal ideal. We can use them to define Weyl divisors and the Weyl divisor class group. There is a version of Spec and Proj that take a quasicoherent sheaf of rings or a quasicoherent sheaf of greater rings to construct new schemes on top of previous ones. This is called relative Spec and relative Proj. We can use these constructions to construct schemes whose rings of global sections is not finally generated, as well as Hirzebruch surfaces, which are ruled surfaces over the projective line, and blowing up. Blowing up is a way to turn a closed immersion into an effective Carrier divisor. The construction involves relative Proj as shown here. It's used to resolve singularities and is also involved in the proof of 27 lines on a cubic surface. Sheaf cohomology is a way to measure how an epimorphism of sheaves does not always lead to a surjective module homomorphism. It gives us a way of constructing a long exact sequence of modules from a short exact sequence of sheaves. It's a very important tool that can be used to study schemes and sheaves on them. For example, it's used to define Euler characteristics, which is then used to define degree in an arithmetic genus. The formula is shown here. A group scheme is a scheme that has morphisms that make it behave like a group. More precisely, it's a group object in the category of schemes. An example is an elliptic curve, since we can add points on it, and they form a group. We can also glue schemes along closed immersions. That is, given two closed immersions with the same domain, the fiber coproduct exists. This allows us to construct schemes with bizarre and unusual properties, such as schemes without closed points and proper non-projective schemes. An important application of scheme theory is number theory. Given an extension of number fields, the inclusion of rings of integers induces a morphism of spec in the opposite direction. This gives a geometric interpretation of many theorems from algebraic number theory. For example, the formula n equals sum ei fi states that every point has the same number of preimages counted with a certain kind of multiplicity. Thank you for watching.